Question 3. Titanium is a transition element in period 3. It is commonly found as TiO2 in the minerals. A. Part 1. Define transition elements. Okay, this is very easy. D block elements that form one or more stable ion with incomplete D subshell. So means not all the D blocks elements, they are transition elements. So for example, for the zinc, after the zinc ionize, it will just form one ion, zinc 2 positive. And for this zinc ion, it has the D10 configuration. Means the D subshell means the D orbitals here, in one D subshell, it has 5 orbitals. So all the D orbitals now, they are fully occupied. So means the D subshell is complete. So we cannot really say that zinc is a transition element then, because the D subshell is complete. In order to be the transition elements, it must be able to form one or more stable ion at the same time. This ion, it must be incomplete D subshell. For example, like the iron 2, once it's formed, we know that it's the D6 configuration, 3D6. So means the D subshell still incomplete. So 1 pair and 4 unpaired electrons. For the iron 3, so it's D5 configuration, so it's still incomplete. So therefore we can say that this iron is the transition elements, because it can form more than one or more stable ions, and at the same time these ions, they're having incomplete D subshell. Part 2. Identify 2 typical properties of transition elements. So you just follow the definition. It must be able to form different ions with different oxidation states, right? So variable oxidation state. And of course, another characteristic of these transition elements is the formation of color compound. So for example, this copper tetrachloride, so it's yellow color. So these are complex ions that form by the transition elements always color, which means the zinc ion not able to form color. So like the zinc oxide is white color, right, white. And of course when it dissolves, it's colorless. Like the zinc nitrate, when zinc nitrate salt dissolve, it will form a colorless solution. Another one is of course is able to form the complex ion like this one, right? And another one that is many of you might not really able to relate is the catalyst. The transition elements, sometimes we will use it as a catalyst. The good example is the iron 2 and iron 3, which used for these reactions between the iodide with the peroxide disulfide or persulfate. So the iron 3 will use to oxidize the iodides to iodine. Then the iron 2 that form will further react with this persulfate. So the iron 2 will oxidize back to iron 3, and this persulfate will reduce to the sulfate. Okay, therefore we know that this is a catalyst, iron 3 regenerated. Part B. The TiO2 positive ions form when TiO2, this titanium dioxide, reacts with excess sulfuric acid. So the TiO2 positive can be reduced by the zinc metal in the acidic condition to form the purple solution, which containing the Ti3 positive, 3i3 positive. Now, part 1. Ti2O2 positive is a colorless ion. So suggest why. In order to answer this, you must be able to identify this electron configuration. The titanium, the electron configuration is the argon 3d2 4s2. So means here there are 4 electrons. 2 electrons in 4s, 2 electrons in 3d. The TiO2 positive ion actually telling you that the oxidation state of titanium is, okay, this is -2. Overall charge is 2 positive, means oxidation state for this titanium must be +4. Means the titanium actually is 4 positive. So means these 4 electrons need to removed, all removes. So now it's from D0 configuration. So means no electrons in the d orbital. So something like this. So means when is formed the complex ion, let's say is formed octahedral, just example. So is, let's say, form 2 sets of d orbitals, okay, the non-degenerate orbitals. So because no electrons in the d orbital and no light will be absorbed. In order to absorb the light, it must be electrons inside the d orbital. So because the d orbitals now is empty, no electrons to absorb the light, no light absorption, therefore has no color formation. Right? That's the theory. Okay, so this is the answer. The titanium is in +4 oxidation state, as I told you just now. So no d electrons in the orbitals or subshell. Therefore, no electrons to absorb the light or photons. No absorption of light. Therefore, we cannot really see certain color. In order to form color, we will needs electrons to absorb certain wavelength, and we will see the complementary color. So no light absorb means all the light pass through, so we'll see colorless. So it's a colorless ions. Part 2. Give the electron configuration of this titanium 3 positive ion. So it's very easy. So refer back to this titanium. Titanium is again is the argon. Argon means this, yeah, this one, argon. Okay, 1s2, 2s2, 2p6, 3s2, 3p6. So because it's the titanium 3 positive, means 3 electrons removed, 2 electrons removed from 4s, 1 electrons removed from 3d, so become 3d1. So therefore is this 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. Part 3. Write the ionic equation for the reductions of the TiO2 positive by zinc metal in acidic condition. If you're not really sure how to construct the ionic equation, so you can do it separately. So let's say you start with the TiO2 positive, this ion. So we know that if you reduce to Ti3 positive, according to the question just now, after that you have to balance oxygen. So on this right hand side, you add H2O to balance oxygen. Then on left hand side, you need to add the H plus to balance the hydrogen. After that, add electrons to balance the charge, because right hand side is the +3. So therefore, you just need to add 1 electrons to make it +3 on left hand side. Okay, the zinc is easy. So zinc, it will get oxidized. So it will form zinc ion and release 2 electrons. So because here is 2 electrons, we must make sure the first half equation also 2 electrons. So this one times 2. Okay, so once it's times 2, then you just sum up left to left, right to right. Okay, of course, cancel the electrons, so you get this OR equation. All right, so you get this. Part C. This part is quite challenging for some of you, so listen carefully. Acidified Ti3 positive reacts with oxygen dissolved in water as shown. So this is the OR equation. Is spontaneous reaction because the Gibbs energy is negative. So from this equation, you should know that oxygens will oxidize the titanium 3 to this TiO2 positive. This is the titanium 4 positive. Yeah? So we know that oxygen will oxidize these ions to form this. Now, the standard reduction potential for the oxygen's half cell means this one is positive 1.23 volt. Now, part 1. Calculate the standard reduction potential of this TiO2 positive, okay, with the Ti3 positive half cell. So first, now you need to get the E0 cell first, means the standard potential for the whole cell, right? After that, you need to use this E0 cell to calculate the E anode. So what is E anode and E cathode? The basic concept must be there. You must know which one is cathode, which one is anode. From this reaction again, we know that oxygens must be the one that oxidize others, means itself get reduced. So means this oxygen's half cell, it must in reduction form, because itself must gains electron and oxidize others. So therefore, this one will stay as reduction form, means it's undergo reduction. When it's a reduction, means it's a cathode. So we know that oxygen's half cell is a cathode. So which means the other's half cell is anode. What is the other half cell? Okay, this one. The TiO2 positive, okay, with the electrons form the Ti3 positive. This is the half cell. Another half cell, because it's asking this, isn't it? TiO2 positive with the Ti3 positive half cell. So this one also in reduction form, but we know that this half cell, it must be an anode. It must undergo oxidation, means it must shift to left. It must undergo oxidation, and therefore this is anode. And in this question is want to find what is the standard reduction potential for this anode, for this half cell. So if you understand what I'm telling you now, then we can proceed to this Gibbs with the E0 cell. Now, this one, no choice, you must memorize and you must know how to use. Delta G equal to negative N F times E0 cell. So N is the numbers of electrons, F is this Faraday constant, and the E0 cell is the one that we need to find. Okay, Gibbs is already given, negative 436.1. So it's equal to negative, so N is 4 electrons, yeah? 4 electrons involved here. 4 electrons, and this one also going to be 4 electrons, right? So 4 electrons involved, and times the Faraday constant, 96500 times the E0 cell over 1000. This one you must put, because the NF E0 cell, this one, after you calculate, is in joule. We need to convert joule to kilojoule, therefore need to divide by 1000. Okay, after that, rearrange, you get E0 cell, which is positive 1.13 volt. So now we already get this. We substitute this value into this E naught cell equal to E cathode minus E anode, right? So this one, and this one already calculated. Cathode is what? Cathode again is the oxygen's half cell here, which is positive 1.23. So is this one minus E anode. So therefore E anode will get positive 0.1 volt, which is the potential, reduction potential for the TiO2 positive with the Ti3 positive. Part 2. When the aqueous citrate ion, okay, this one, are added to the Ti3 positive, so a complex ions form, right? This complex ion. Explain in terms of d orbitals why the Ti3 positive is able to form this complex ion. Okay, it's very easy. First, you need to know the configuration of this Ti3 positive. I already told you just now, is argon 3d1. 3d1 means one electrons occupied in one d orbital, the rest is all empty. So these empty orbitals actually it can gains or it can form dative bonds with the ligand. Means it can accommodate the electrons from the or lone pair from the ligand. Then it's form bonding. So that's why we say that Ti3 positive has empty d orbitals, which can use to form dative bonds with the ligand. Because ligand is a lone pair donor, and it can form dative bonds, right? So in order to form dative bond, it must be a place there. So the place is the empty d orbitals. Or you can say the Ti3 positive has awakened d orbitals, empty d orbitals, which are energetically accessible, because now the d orbitals is at the highest energy level, so it's more accessible, so it can form dative bond, easily form dative bond with the ligand. Okay, now part 3. Acidified this titanium, this complex ion that mentioned just now, right? This one. So does not react with oxygen dissolved in water like the Ti3 positive just now. So means this one will not react with oxygen, means it will not get oxidized by oxygen. Suggest what is this means for the values of the standard reduction potential for the following half cell. So it's actually quite easy and quite straightforward. It is actually because of this standard reduction potential is more positive than what? Than the oxygen half cell. Because when this is more positive, then it will stay as reduction form, so it won't go left hand side, or it will not shift left, right? In order for this complex ion to react, so it must be oxidized, right? It must go left. It cannot go left because the potential is actually larger than 1.23, so it will stay as this reduction form, it won't shift left. That's the reason why, right? So it means in order for this to dissolve, it must shift left, get oxidized, release electron. If not, means it will stay at this reduction form, which means its standard reduction potential, it will be more positive than this oxygen half cell. Okay, I hope you understand. Part D. Some reactions of titanium dioxide shown in this figure 3.1. So this is the reactions. The anion AC negative, actually we in full name we call acetyl acetonate ion. This one AC. So it's a bidentate ligand, means it has two donor atom, donates two lone pair to form two dative bonds with the metal cation. In this case, is a titanium. Now, let's start with the part 1. The titanium ion in the TiF6 2 negative, this one, and the TiACAC2 Cl2, this one. Okay, they're having the coordination number 6. So what means by coordination number? Very easy. As you can see, both complex ion, they are octahedral complex ion, and they're having the 6 dative bond. 1, 2, 3, 4, 5, 6. So because it's formed 6 dative bonds with the metal cation, so therefore we know that the coordination number is 6. So very easy, the numbers of coordinate or dative bonds being formed by the metal ion with the ligands. Part 2. Write an equation for the formation of this TiF6 negative from TiO2. Very easy, look carefully. TiO2 react with HF from the TiF6 negative. So we know that all the oxygens must out and reacts with hydrogen from H2O, and the remaining hydrogen will be H+, so it's 2H+ here. So means at the end it will form this complex ion with 2H2O and 2H+. You can actually combine these two to form hydronium ion, 2H3O positive. Part 3. State what is means by bidentate ligand. Very easy definition. The species with 2 lone pair of electrons, normally we will just say 2 lone pair. No need to say 2 lone pair of electrons. 2 lone pair means the pair of electrons, right? That form the covalence bond with central metal ion. Okay, as easy as this. Part 4. So now TiACAC, okay, 2, and the chlorine, the Cl2, both optical shows both opticals and geometrical isomerism. So means this complex, it can show this and this isomerism, and therefore it can exist as 3 stereoisomer. Now in figure 3.2, already given one isomer, which is a cis isomer. Why? How we know it's cis? Okay, we look at the monodentate ligand, the chloride. So this chloride, they are actually at the same side, means the bond angle of Cl, TiCl is 90. So we know that this one is a cis isomer. So remember, the cis isomer, they will form optical isomers as well. Means, let's say now we draw a mirror and the mirror image. So the mirror image of this cis isomer is this, right? So you must follow lah. In this drawing, is slightly different from what we did so far. So is actually in this drawing, in this figure 3.2, is 4 normal line which they are in the same plane, and this which line is the one that show this chloride is in front. This dash or this dotted line is at the back. So it's actually same thing. It's a 3D drawing. So since it's drawn like that, then we just follow. So we draw 4 normal lines and 1 dotted line at the back and 1 wedge line in front. We just follow this position, chlorine here with this chlorine with this, AC, okay, this one with this, and this one with this, right? So therefore, now we have the mirror image. So these mirror images, they are non-superimposable. Means this and this, they are both cis isomer and they are mirror images, they are not superimposable. Means they are stereoisomer, means optical isomer. So means you just need to put this optical isomer to isomer 2, right? So exactly the same thing, right? So after that, you need to draw another one, the trans isomer. So you just start with this chloride You put chloride opposite. After that, you continue with the acid, right? So you get this trans isomer. So because the chlorine, titanium, and chlorine, the bond angle is 180. Okay, last part. The AC, the anion is symmetrical. Deduce which, if any, of a stereoisomer 1, 2, 3 in the part 4 just now are polar. So this one has to depends on what you put. In my drawing, so as you can see, the stereoisomer 3 is non-polar. Why? Because the typo can cancel. Okay, opposite is the same ligand, you see, so it can cancel typo. This one also can cancel its typo, right? That's why this is non-polar. For this cis isomer, this cis and this cis actually no mirror images, but in terms of this dipole cancel or polar or non-polar, so they are actually similar. Because you see opposite here, this is chloride, this is AC, so it's different ligand, so it's different thing. The dipole will not really cancel. So therefore we know that isomer 1 and isomer 2 here, these two will be a polar. So it's these polar isomers or polar stereoisomers. So therefore you just need to mention which one. Okay, so in my drawing is stereoisomer 1 and 2. So both polar. Why? Because dipole do not cancel. Okay, that's all. Okay, thank you.